Class example 3.5.3. Look at those lovely caribou over there. There's a linear relationship between the number of caribou, which is N, in a herd, and the number of caribou legs, which is L, which represents a model of this relation. So first of all, let's just think about what N is. N is equaling to the number of caribou. This is going to be our independent, INDEPE, variable, because the number of caribou dictates how many legs there are, which is L. And so we know we're going to have an input of N and an output of L, right? Number of caribou dictates the number of legs. So let's just quickly do a 0, 1, 2, and 3 before I keep looking at this. If I have no caribou, I have no legs. If I have 1 caribou, I should have 4 legs. If I have 2 caribou, I should have 8. If I have 3, I should have 12. And we can go from there, okay? So this is kind of what we're looking for, or some version of it. We'll have to see there, what the numbers are. Okay, so let's look at A. It says the number of legs is equaling to 4 times the number of caribou. That's exactly how I got this at this table, right? 1 times the number of 4 gave me 4. 2 times the number 4 gave me 8. 3 times the number 4. So definitely A shows the situation. B, we even have a couple of our table of values here. So we've got 0 caribou, 0 legs. That works. If we have 3 caribou, we times that by 4. Each caribou having 4 legs, that's 12. If we had 8 caribou, we would times that by 4. So that gives us to 32 legs. If we had 15 caribou, we could times that by 4. And we've got definitely 60 and 50 times 4. So B, larger numbers than what we have in the table, but still 4 legs for every caribou. Question part C says I'm going to take the number of caribou and add 4. So let's just see if that's going to equal to the legs. If I had 0 caribou, I would have then 4 legs. That already doesn't make any sense. So this one is not representing our situation here. Okay, let's look at this one. It says number of caribou along the x-axis, which we already know was our input. Number of legs is going up the y-axis. And so it looks like if I said 5, 10, 15, 20, and then it looks like I've got 10, oops, sorry, that's 20, not 10, 20, 40, 60. So if I had 5 caribou, do I get 20 legs? Well, yes, that would make sense. 5 times 4 is 20. If I had 10 caribou, I would have 10 times 4 is 40. This is great. That's awesome. Everything's going really, really well. But here's the problem. This is a connected line. And a connected line indicates that we can have any number in the element of the reals, right? So we should be able to say that the number of caribou is an element of the reals if we have a connected line. But I've never seen half a caribou that's alive. Let's put it that way. So we can have 1 caribou, we can have 2 caribous, we can have 3 caribous, we can have whole numbers of caribous. We can even have 0, right? So we can have whole numbers represented in our graph, but you can't have 1.1 or I don't know, 3.752891 caribou or pi caribous. This does not make any sense. So it's not part of the reals, which means that this graph cannot represent it because it is connected. So let's look at E on the other hand. It looks like it's going up by the same scale, and we said that the individual points that were here made sense. And I can also see that these dots are not connected and they're only representing whole lines. And because we've already checked 10 caribou times 4 legs each is 40 numbers of legs, then we should be good to go. E is good. It is part of the winner circle. Okay. F, if we have 3 caribou, we have 6 legs? Nope, that doesn't make sense. So although this looks like it's a linear pattern for F, we can't have 3 caribou and 6 legs. We have to have 3 caribou and 12 legs. So our answers are going to be A, which is the function, B, which is just a list of values, random values, and E, which is a graph representing the same scenario with just larger quantities.